Alright, so first of all, in this video I want to discuss one of the homework questions with you, because I've noticed most people had questions about this one in the past, so I want to discuss it with you. This is homework 6. Homework 6, question 2, 23.73, okay? This is still electric potential from a continuous charge distribution. Okay, as I said, the continuous distribution of charge is like the hardest part in this class because it uses a different mathematical tool, integral, right? It's not algebra. That's why people feel it's hard. You just need to practice, right? The only way, okay, to be good at something is just practice a lot. Okay. Now let's take a look at this question. So we have a rod here, and then the problem already sets up the coordinate system for us, okay, which makes things a little bit easier. This rod has a length A. It carries a total charge Q, right? Positive. All positive, okay, and then we want to actually find the potential at two different points, but we're going to use the same theory. The theory is the same. So the first point we want to find is the point P, which has a distance B from the right end of the rod. So this point P, which has a distance B from the right end, okay. Now this is a continuous charge distribution, right? You can't just use plug numbers into an equation to find that, right? You have to use the integral to integrate the dV along this rod, right? So the idea is this: pick a dq here. Let's call this guy dq, a small element. That's why we call it dq. This d is a differential symbol, right? It just means it's infinitely small. That's what this d means, right? So this guy is going to create a potential here, dV. And then all you need to do, the net potential at this point, you're going to add these dVs together, right? Each dq you pick, right? I can pick a dq here, 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 here. You're going to add all these dVs together. Right? At the end, you have an infinite number of dVs. Right? That's why the sum becomes integral. Now, so this is the fundamental theory, right? And then, how do you write this dV created by dq? I can still use the theory for a point charge. Right? For a point charge, we derived this. Okay, now you call the charge dq, you're just changing the symbol, right? It doesn't matter. I'm just going to write it down, dq over r. Now, our goal is always the same, right? I want to write this integral. First of all, I want to take all the constants out possible. Secondly, I want to write anything changing in terms of one variable. Then I can look it up in the integral table, okay? So Ke, you can always take it out, constant. Now dq over r. Now what is this r? R has a definition, right? The r is always defined, not radius in this case, the r is always defined as distance from the source charge to the point you want to calculate the potential, okay? So if I pick a dq here, this, it's going to be the r. Right, because I'm trying to find the potential at this point, right? And if I pick a point, say this guy, this is going to be my r, right? So you see that the r is definitely a variable. You can't take it out, right? You have to leave it there, okay? So dq is something you're going to integrate. So okay, now my goal is this: I want to write r and dq in terms of one variable, okay? So which variable do I pick? Remember, dq, we have seen this guy many times, right? If it's a rod or one-dimensional charge distribution, I can always write dq as linear charge density times the very, very small length of this one-dimensional charge distribution, right? This is a density. You multiply the density by the length, right? Linear charge density. It's like when you find some mass, something, the mass of water, you do density of water times the volume, right? So it doesn't matter if the volume is too small, right? If the volume is really small, I can still use this theory to find the mass of a certain water you give me, right? So we just take a limit that everything becomes extremely small, infinitely small. But this theory is true, still true. I have the linear charge density, which is the total charge divided by the total length of this one-dimensional charge distribution. And then multiply that by the small length of this very small segment I pick. Now in this case, lambda e is not given, right? The problem only gives you these symbols. So, okay, so I can write this lambda e as q over the length. What is the length of this charge distribution? It's a, right? Because this is the rod. This rod carries charge, and the length of the rod is a. Okay, so this is going to be what I plug in at the end, right? Well, you can carry if you like, right? But when I do algebra, I want to keep things as simple as possible, right? I can plug everything back in at the end, okay? And then this dl, we have seen that many times, right? I can keep that if it's like a circle or something like that. But if it's a rod in x or y direction, I can replace it with x and y because I feel more comfortable working with x and y, right? So in this case, this guy is in x direction. So why don't we just replace this with dx? Okay, so that's my first step. I would write this dq, and we have done that many times, always as a linear charge density times dl. And then depending on what axis is on, I can write it as dx or dy. Or if you like, you just carry dx. You just call this axis L. You call this axis N. Is there anything wrong? You tell me that I just call horizontal L, call this name L, call this name N. No, there's nothing wrong. But people feel more comfortable working with things they are familiar with. So that's why when we see a horizontal axis, okay, let's call it X. When we see a Y, when we see a vertical axis, we call it Y. Okay? So, all right. So to make us more comfortable, we still call this X, and this becomes X. So the next thing I should do, so we have some experience now. If I can write this R in terms of X, then everything is going to be in X. So I should be able to find out the integral in the integral table, right? So how do you write the R in terms of X? Remember, this R is the distance from the dq to the point you pick, right? So in this case, it's gonna be, how do I connect this R with X? Well, it totally depends on where you set up your coordinate, right? If you use the coordinate system set up in the problem, so this is a coordinate, okay? So remember, you're gonna integrate the whole rod, okay? So the X is gonna be the X coordinate of every single dq here. So you have everything to the left, okay? On the left of this q. So let's call this guy positive X. Because I don't want to deal with negative numbers, okay? A lot of people, they're afraid of negative numbers, okay? So again, there's nothing wrong if you call left positive, right? Nothing wrong, okay? So in that case, how would I draw X, okay? So if this is dq, which distance do I call X of the X coordinate of this dq? Of course, this is what I'm gonna call X. Right? You see that if I tell you this is the axis, this is the x-axis, dq is here at 5 centimeters. Oh, you're just telling me dq is 5 centimeters from the origin. Where's the origin? This is the origin. So if I tell you the x coordinate of this dq, you know that's the distance, right? If I tell you pick a dq here, what is the x? This is going to be the x. So what is the x? A connection between x and r. How do I write r in terms of x? Take a look at this. If I pick this dq, this is going to be the r I use in that equation, integral. How do I write this r in terms of x? Hey, look at this. R equals the sum of x and this distance. What is this distance? B. Okay? So it looks like for this dq, I can write r as x plus b. Is this true for any point? Take a look at this point. If I pick this as dq, this is going to be the x, because this is origin. I say this is a positive x. And then this is r I need, right? Remember, r is always the distance from the dq you pick to the point you want to calculate the potential. This is r. What is the relation between x and r? Oh, still x plus b equals r. Okay, so that's how I write r in terms of x, right? If this is the coordinate system I set up. Nice, okay? So I'm just going to write down r in terms of x plus b. Now I'm ready, right? So I'm going to do, so I only have dx over x plus b. Now you can look this up in the integral table, okay? And this is actually a very simple one, okay? What are the bounds? Remember the bounds, it's going to be the bound of this, the minimum and the maximum value of this dq you pick on this rod. So you should go from this point to this point. This is rod. You are integrating, remember, you're integrating on this rod. You're not integrating here, right? There's nothing here. What are you integrating, right? You always integrate the dq on this rod. So what is the minimum value of x you can get on this rod? Of course here, right? If I pick a dq here, the x value I can get is going to be 0. What is the maximum x value you can get on this rod? Well, it's going to be this. And if I pick this dq, what is the x value I can get? The whole length of this rod, right? This is going to be a. So the bounds is going to be from 0 to a, okay? Of course, this totally depends on where you pick your origin, right? You can also say you pick the origin here. So the value is going to become b to b plus a, right? So these bounds are totally arbitrary because they're all coordinates, right? It totally depends on where your coordinate, where your origin is. I pick this as origin, okay? So that's why the bounds are going from 0 to a, and I also call that positive because I don't like negative numbers, okay? Okay, now you can go ahead and plug bounds in and then find the integral. Now I can put this back in, right? So this lambda is q over a, right? So at the end, I think you should get some natural log minus something, and then you can put them together using this equation, right? Natural log a minus b equals natural log m over n. Okay, so you can make it a little bit nicer. Okay, so that's your final answer should be in that form, right? Something times natural log times something divided by another thing. All right. So that's point B. Now, what about point C, which is at the top? Okay. So now we're done with this. I'm gonna redraw it because I don't need that anymore. I don't want to make it too messy. I still have this rod, positive charge uniformly, right? Now this length is A. Now I'm looking for the potential created by this rod at that point, okay? This point has a distance C, okay, from the origin, if I still use this as origin. Okay, let's see. This is still potential due to a continuous charge distribution. I'm still gonna use the same theory, right? Pick a dq, doesn't matter, let's call this guy dq. So I would have this equals the dv, right, integral of this dv. This dq is gonna produce a potential here I call dv. No arrows, right, no vectors, it's just gonna be a number. Integrate it out, you get this, nothing changes. I take out ke, right, that's the theory. The theory never changes, right? The math can be different. The theory is always the same. That's why I like physics, okay? I don't need to come up with my own theory. I don't have 1,000 theories to learn when I see different cases, okay? You take that out, now you see that this is still true because I can always write dq as the linear charge density times dl, and I'm still gonna call this x-axis, right? You see that this is still true. It doesn't matter which point you want to calculate. You want to calculate this point, this point, or this point, or this point, or this point, doesn't matter, right? Because the charge is still here. The dq I still pick on this charge. So this doesn't change. So the only thing that changes is going to be this, right? So after this point, everything is going to be different. Okay, but the theory is still the same. So my goal is still this. I want to write the r in terms of x so that I can integrate out with this dx. Okay, so how do I write the r in terms of x when I pick this point? Again, let's draw r, right? R has a definition. Everything has definition. From the source charge to the point you want to calculate the potential. This is source charge. So that's going to be the r. How do I find this r? Well, okay, obviously there's a right triangle I can use here. So the r is going to be square root c squared plus this side squared. What is this side? Well, we just figured that. If I set this as my origin, right, this side is just going to be the x coordinate of this dq, right? Whatever this x coordinate is, it's just telling you the distance from the origin to this point is this value. So this is just going to be c squared plus x squared. Okay, that's what we need, right? Plug it in. C squared plus x squared. Now take out this lambda e. Now if you like, you can replace it with q over a, right? Now you see that you can carry this q over a if you like, okay? You don't want to carry this lambda e. Now I would have dx over c squared plus x squared and square root. That's all, right? Now you can look this up in the input table. What are the bounds? Still the same. Remember, the bounds are just the dq on this rod. Has nothing to do with this guy, right? You pick this guy, you pick this guy, you pick this guy. The bounds for this integral, because I'm still integrating everything here. So the bounds for the x, if this is still my origin, this is still my positive x-axis, still from 0 to a. Right? So the only thing that changes is the expression for the r, because now you pick a different point, right? So now you see that you can go ahead, look this up, and then put the bounds in, and then try to simplify a little bit, okay? In this case, you're gonna still get a natural log, okay? You're gonna still make the use of this thing, I believe, and then put everything together in a very nice form. So that's gonna be your final answer, okay? So that's that. So you see that in principle, right? You see any kind of charge distribution, right? So just take a look at this rod, okay? If you want to calculate the electric field at this point, we just did that. If you want to calculate electric field at this point, we just did that. If you want to calculate, you can also do that point, or that point, or that point, right? See that? In principle, for this rod, you can calculate the potential. You can map out the potential at every point, right, in this region. So you pretty much, you know all the information about the electric field. You know that. You already know that, right? So that's the theory, okay? Of course, I'm not going to do that here, right? Because that's going to take a lot of work. Even if I want to do that, right, I can. But we have already found the theory, right? Okay? What we did in class is actually this point, right? If you rotate it 90 degrees, it's going to be a point, a distance d from the center of the rod, right? You see that actually you can find any point. It doesn't have to be this point, this special point. You pick any point, okay, in this region. You can always find the potential, right? So we have found the fundamental theory. So we are done, right? Calculating the potential at every point, yeah, that's just some detail I can work out, okay? But as a physicist, my job is done. I already found the theory, all right? So yeah, that's the question I want to go over with you. Now we're gonna move on to a new topic. So this is PowerPoint 7. We're gonna discuss capacitors. Capacitors is gonna be the first circuit element we discuss in this class. We're gonna also discuss resistors after this, okay? But capacitors, because we have already seen capacitors, so we want to discuss capacitors first, even though people are more familiar with resistors, but we can leave that after the capacitors. We discussed parallel plate capacitors, right? That's how we set up uniform electric field in real life, right? You grab two plates, you charge them with opposite charges, the same amount. The electric field is always going to be from positive plate to negative plate, very uniform, right? So that's called a capacitor. So actually, a capacitor is a device, so it doesn't have to be two parallel plates. Any conductors that can carry charge, right? You put them together. You have two of them. You put them together. You can call them capacitors. Okay. So a capacitor is just a device to store electric potential energy and electric charge. Why do we want to store them? Because we want to use them at a later time. I don't want to use that now, right? I have a water bottle. I use a water bottle to save, to store water. Why? Because I may need to drink it, after this video, right? When I'm thirsty, when my throat hurts, okay? So you see that the use of this bottle is to store water, right? So the use of a capacitor is to store electric charge and potential energy, because we don't see that, okay? So I feel it's a little bit weird. It's not weird, right? We just want to save that for later use. Okay? And I'm going to tell you some applications of capacitors, okay, after we have finished the theory. So you can see capacitors, they're actually very widely used in everyday life, right? Electronic flash units, lasers, airbag sensors, everything, radio, television receivers. We're going to see why it can be used in radio, television receivers at the very end of this semester, okay? Okay, so as I said, actually, in a general sense, any two conductors, you pair them up, okay? And you can always store charges on them, so that's a capacitor, okay? And then, of course, the capacitor, now we want to define something, okay? That's conceptual, okay? I understand that. You can always use two conductors to save some charge and electric potential energy, right? Because the electric field carries potential energy. We learned that. Now we want to define something so we can, again, make predictions. We can explain experimental results, okay? Now we define a thing called capacitance because for any particular capacitor, the ratio of the charge to the potential difference, it's always a constant, okay? So it's a property of this capacitor. So if it's a property, when something is a constant, something is a property, it deserves a name, okay? So we define it as the capacitance. We call it capacitance. We define it as the charge on each conductor divided by the potential difference, okay? Because if you have two conductors, right? This is positive, this is negative, okay? No, two conductors, not two charges, okay? Like doesn't have to be like a power plate. If there's these two conductors, right, there's always an electric field between them, right? In this case, it's not going to be uniform, right? It can be something like this. So if there's an electric field, you can always calculate the potential difference between them, right? Always, right? It's going to be hard, right? But theoretically, there must be a potential difference between them. If you charge them with the same amount of charge, right, you can always have a potential difference between them. So, and then we found out that if you divide the charge by the potential difference, you always get a constant value. That means if you double the charge on each conductor, this potential between them is going to be doubled automatically, spontaneously. You don't need to do anything, right? And then if you reduce the charge by a factor of 2 on each conductor, the potential difference between them is also going to be reduced by a factor of 2. So that's why the ratio between them is going to be constant, okay? So, okay, it's a constant, it's going to be a property of this capacitor, we call it capacitance. So the unit for this guy is going to be coulombs per volt, right? Okay, so now we're again using the same symbol for different things. This is a symbol for capacitance, okay? This is a symbol for coulomb, for the unit, so don't get confused by them, right? And we do have a new name for this guy. We call it Farad in honor of Michael Faraday. Okay. Okay. So so Farad is the SI unit of capacitance. Okay. Of course, the simplest capacitor is the parallel plate capacitor, and that's what we're going to discuss in this class. Okay. And then, if this is the definition of a capacitance, right, we can, and then we work on a parallel plate capacitor, simplest capacitor, okay, we can find another special equation for parallel plate capacitor, right? So all we need to do is just to use all the equations we know about parallel plate capacitor, right? So for example, we already know the electric field parallel plate capacitor is going to be sigma E over epsilon naught, right? We know this, and we also know that, and the sigma E, of course, is going to be the charge on each plate divided by the area of each plate. Now, the potential difference between them, if it's a parallel plate capacitor, the electric field, the electric field between them is always going to be uniform, right? If it's uniform, I can use the theory we learned earlier, which is E times D. And now the D is just the distance between these two parallel plates. Okay? Now let's put everything together in this equation, this general definition. Okay? So I would have C equals Q over this. Now Q, let's put this guy here, E times D. Okay? Now this Q is going to be sigma E times A. And sigma E is going to be E times epsilon naught, so I can get E times epsilon naught times A divided by E times D. And now that's going to get rid of this E for me, right? So at the end, I get a very nice equation, epsilon naught times the area divided by the distance. Okay? So you see that this is a general definition of capacitance. For any two conductors, you can make a capacitor. That's how you define capacitance. But for parallel plate capacitors, we have a very nice, easy equation to calculate these capacitance explicitly, which is this equation, epsilon naught A over D. So this equation is also going to be given on the test. I don't need you to derive this. Okay. And then you can, from this equation, you can understand why the C is a property of this capacitor. Epsilon naught is going to be constant. The area, if you have two parallel plates plates, you make a capacitor out of them. The area is going to be a product of this each plate, right? It's not going to change unless you get a different plate. And the distance, right? Once I make these two guys as a capacitor, right? I fix the distance between them. All these three numbers, they're not going to change, right? So it's going to become a property, a constant for this parallel plate capacitor. Okay, so that's why this C capacitance is going to be a constant for a specific capacitor. That's why we define it. Okay, so the capacitance only depends on the area and the distance. So it's going to, once you fix these two numbers, it's going to be a property of this parallel plate capacitor. So when we draw a symbol, when we draw a capacitor in a circuit, okay, we just draw two vertical lines, right? So we're going to discuss circuits later, okay? Circuits are fun. They just look like two vertical lines. Well, it doesn't have to be vertical, right? If you have a circuit like this, you can draw it like this. Okay? Two parallel lines. All right, so that's that. So this capacitance, C, is a measure of the ability of the capacitor to store electric charge and energy. Why is that? Okay? So think about it, okay? If you rearrange this equation, what do you get? You would get Q equals C times delta V, right? So I always tell my students use this water tank to help them understand the relation between these three guys, right? If you have a water tank, right? So the area, right, is already fixed, right? You can't change the area of the water tank unless you get a different water tank. But if you put more water in it, right, the water level is going to get higher and higher, right? But the area, the base area doesn't change because the base area is a property of that, right? And then if the water level is higher, that means the water stores, it's going to get more and more, but the A is going to be the same, right? But if you want to say, I have a lot of water to store, I'm just going to get a water tank with a bigger area, right? So I can put more water in it, right? So this C is pretty much like the area of this water tank, right? So it's going to be a constant, right? It's going to measure its ability to store electric charge, right? You see that if the C is big, right, that means for a certain potential difference, it's going to store a lot of charge than a capacitor with a smaller C, right? So the C is pretty much like the area of the water tank, right? The V potential is pretty much like the water level, okay? And then this V, the Q, is pretty much like the volume of the water in this water tank, right? So this volume is going to change with the water level, the height of the water level, but the area is not going to change. It's a property of this water tank, right? If you want to store a lot of water, you would get a water tank with a very big area, base area, right? So that's pretty much like this C, right? So the C measures the ability of the, if you want to store a lot of charge, I would get a capacitor with a very large capacitance, right? So that's why the capacitance is a measure of the ability of the capacitor to store electric charge and energy. It's because we don't see them, so it looks a little bit weird to us, but compare this with the water tank, okay, you know what it means, right? Now let's see. I want you to use this question on slide 5 to practice this general definition of the capacitance and this derived equation for owning parallel plate capacitance. So let's take a look at this question. 3 meters times 5 centimeters, 3 centimeters times 5 centimeters plate are spaced 2 millimeters apart. If the electrodes are connected to a 125 volt battery, what is the magnitude of a charge on each electrode? Okay, so we want to find the charge on each electrode, which is just going to be the Q in this equation. Okay, so that means I can rearrange that because I have a capacitor, right? If I know the capacitance and the potential difference between them, I multiply them together. And I do have the potential difference between them, right? Because you already connect these two electrodes to a 125 volt battery. That's the 125 volt, right? So all I need is this capacitance of this capacitor. How do I find this capacitance? Well, because they are parallel plates. So I can go ahead and use this special equation, because this is only true for parallel plate capacitor. I can use this equation to find out the capacitance of this parallel plate capacitor, and then use the general definition to find the charge on each electrode. Okay? So now you can pause the video, go ahead and find that. All right, so what is your number you got? So the C, if you use this equation, right, because you already know it's going to be 3 centimeters times 5 centimeters, that's the area. And then the distance is 2 millimeters. And the epsilon naught is constant, right? Epsilon naught is 8.85 times 10 to the negative 12. Okay? So, and then you use this C multiplied by the voltage, you get the potential difference. You get, oh, this number I got, this C I got, if I put all the numbers in, 6.64 times 10 to the negative 12 farad, okay? So farad is actually a very large unit, okay? If you want to make a capacitor with 1 farad, that's actually very hard, okay? So usually the capacitors you see in everyday life, they're very small numbers. They're like microfarads or picofarad, like this, 10 to the negative 12. That's a typical value of the capacitors. we use in everyday life, okay? So if you solve a problem, you get a capacitance like 1,000 farads, or 10 to the 5th, okay, you have done something wrong. Okay, check your algebra. You shouldn't get that large number. Okay. Now you multiply them together. Okay, so you will get the charge. Okay, so that's the right answer. 8.30 times 10 to the negative 10. All right. So as I said, the use of these capacitors is to store charge and energy for later use, okay? And why do we want to do that? I'm going to tell you some applications, okay, at the end. So, okay, if you want to then, and I know that the capacitance is the measure of the ability for these capacitors to store electric charge and energy. So that means if I want to always store more charge and more energy, right, I should make this C as large as possible. I should do everything possible to make the C large, right? So when I make a capacitor, okay, I should always try to make everything, okay, try to increase this C, okay? So, and then you see that by looking at this equation, if I just make parallel plate capacitor, right, there are two ways to make this C larger. You increase this or decrease this. So that means you put them very, very close to each other, right? So that's going to make this C large. It's going to store more charge. And then you make this area big. But making area big, that's not a good idea, right? Because you don't want to make it if you want to, because remember, these are circuit elements. You want to make these circuit elements small so that you can make a circuit, right? So, and then this guy, there's not much you can do. You already put them very close together, right? So these are the real capacitors you see in everyday life. There's also an image on this picture on this slide, right? So usually we put these two plates very close to each other and then roll them up in a cylinder, okay? So we don't have two sheets this way. Why do we do that? To save space, right? You roll them up, it becomes a cylinder, okay? Isn't that smart? So then is there another way to, so you already put them very close to each other, right, when you roll them up in a cylinder, okay? So is there any other way I can make this C larger, right? We always want to find other ways to make this thing larger so it can store more charge and energy. So another way, and which is very effective, it has other benefits, is to put some insulators between these plates, right? Take a look at this image at the top, right? So you still have two parallel plates like conductors, very thin. You make them very thin because you want to make them small, right? Then you put some insulators between them, and then you roll them up, okay? So first of all, it's gonna increase the capacitance, okay? Okay, by putting insulators between them, it's gonna increase the capacitance, okay? Which is not that intuitive, right? You would guess put insulators between. How come that? It's going to increase their ability to store charge. We're going to see that. So at the same time, it's going to also increase the breakdown voltage, which is the maximum voltage the capacitor can take before it breaks down, okay? Because you don't want to damage that, right? If the voltage is too high, you may damage this capacitor. And also, it's going to maintain this, it's going to make sure these two metal sheets, they are not in actual contact, right? Because if they are in actual contact, then these two plates, if one carries positive charge, the other carries negative, all these charges are going to be neutralized, right? So it's going to get discharged. So you don't have them separate, you don't have them saved, right? They're going to get discharged. So that's why dielectrics is widely used in capacitors to make them capacitance bigger, increase the breakdown voltage, and also maintain these parallel plates without actual contact. Make sure they don't get discharged. Okay? So now let's see why this is going to increase the capacitance, actually. It's very interesting. So take a look at the image on slide 7. Okay? So by putting insulators between two parallel plates, it's actually going to reduce the electric field between them, okay? So it's going to make the electric field weaker. That's actually easy to understand, right? So you have a positive and negative plate, say, and you put some insulator. So the electric field between them, say, it's going to become E. And how come that you put some insulators between them, the electric field is going to be weaker? Well, okay, I hope this is intuitive, right? You put insulators between them, so it's going to make the electric field weaker. But how is that true? Because if you put the electric field between these two plates, created by these two plates, is still E, right? So let's call it E naught. But now if you have some insulators here, you put some insulators here. Remember, these insulators, they can be polarized. This is the electric polarization we discussed at the very beginning of this class, right? Remember the soda can and the rod, the demo. Did you do that at home? Okay. So this guy is going to be polarized. So what is the result? The result is this. So all these atoms, they're going to polarize. So the negative charge is going to be a little bit closer to that, and positive charge is going to be a little bit close to that plate, right? So at the end, you see that there will also be a net electric field created by all these polarized atoms in this direction. It's going to be weak, right? But because the positive charge, they are sort of separated, okay, a little bit, okay? So this is going to be electric field, this is going to be electric field, electric field, electric field. So at the end, you will have a net electric field in that direction. So let's call that E prime, whatever you want to call it. So the net electric field in this region, now it's going to become E naught minus E prime, right? So of course it's going to get weaker, right, compared to nothing between them, right? So this is going to be definitely weaker than E naught. So by putting insulators between these two parallel plates, it's going to reduce the electric field. And there's a theory, okay? If you put the insulators between them, the electric field is going to become the electric field with nothing between them, only air or vacuum, divided by a factor K. Okay, so that's a theory. This K is called dielectric constant. Okay, so it's a constant, it deserves a name. We call it dielectric constant. It doesn't have a unit. Of course, it shouldn't have a unit, right? These two guys have the same unit. This has to be a pure number. So, and then it's always greater than 1, right? Because this E is going to be smaller than E naught. So this K is going to be greater than 1, of course. And if that gets larger, now you see that the C in this case, okay, if I use the definition, C is still going to be charge over potential, right? Now the charge doesn't change. The charge still stays on each plate. But now so this is the C, let's call it C naught. It's going to be Q over V naught. It's going to be Q over E naught times D, right? Now, if you put insulators between them, Q is still the same, but the potential is become the new electric field times D, but the new electric field is smaller than E naught. So this guy is going to be actually greater than C naught, right? Because the E is at the bottom, okay? This guy becomes smaller, it's going to make the whole value bigger, okay? So that is why by putting insulators, okay? Dielectrics are just a fancy name for insulator. By putting insulators between these two parallel plates, you actually make the C larger if this is a capacitor you make, okay? All right? So, and then of course, if you have this C naught divided by K here, then it's just going to increase the C naught by a factor of K, right? So by putting dielectrics between these two plates, you actually get this C increased by a factor of K. So this K is the dielectric constant, okay? So it's a property of different material. So you can take a look at the table on slide 8 for different materials. The K can be measured experimentally, okay? So let's see, and then as I said, by putting insulators between these two parallel plates also has other benefits, okay? Another benefit is that it's going to increase the breakdown voltage of the capacitor. So first of all, why is that good? Well, okay, because if you want to use this guy to store charge, right, and then you're going to do Q equals C times delta V. By putting dielectrics between them, you can increase the C. But if at the same time you can increase the maximum voltage it can take, so that means you can increase the charge it can store even more, right? Because it's a capacitor, okay? There's insulators between them, okay? So the insulator is going to become a conductor at a certain high voltage. That's called dielectric breakdown, right? So like things around us, they are normal. They are insulators at normal conditions. They may become conductors, and when the electric field in them, it's really high. That's called a dielectric breakdown. Okay. So for example, think about air. Right. Lightning is a real life example of dielectric breakdown. Okay. Why? Because air usually is a very good insulator. Right. You never conduct electricity using air. Right. I know that air doesn't conduct electricity. Right. But if the electric field, okay, inside this air, okay, becomes really strong, okay, so the force, electric force becomes so strong, it's going to tear these electrons apart from these atoms. So it's going to ionize the air, okay, it's going to ionize the air, and then the air is going to become conducting. So it's not an insulator anymore, it breaks down as an insulator. So that's called a dielectric breakdown, right? So usually that's going to come with lightning. When you see a lightning, that's a discharge. That's a quick discharge, okay? Very quick discharge. So that is, so you see that insulators, they have a certain maximum voltage they can take and maximum electric field they can take before they break down, before they become insulators, okay? So, and that's called dielectric strength, okay? That's the maximum electric field a material can withstand without breakdown. So that's just a fancy name for Emax, okay? Dielectric strength is the fancy name for the Emax any material can take before it breaks down as an insulator, okay? So take a look at this, the table of the dielectric strength and dielectric constant on slide 10. Right, so you see that air, the maximum electric field air can take before it breaks down, before it becomes insulated, before it ionizes and become an insulator, it's 3 million volts per meter. Okay, so that's very high. That's why normally air is a good conductor, right? But you can check other things, other materials, they have even better dielectric strength. Right. So if you use them put them between these two plates, that means you can even use these capacitors in a higher, connect them to a higher voltage, so it can store more charge for you, right? So by putting insulators between parallel plates, you can increase the capacitance by a factor of K, which is called the dielectric constant. Okay. You can also increase the maximum voltage, breakdown voltage the capacitor can take before it's damaged, before it becomes before the insulator between them becomes conducting. Okay, so that's why we use dielectrics in capacitors. Okay, so we're gonna see some examples next time. You're gonna see. I'm gonna show you some numbers so you can see why by putting insulators between two parallel plates, it's going to increase the charge it can store, okay? That's what we're going to do next time. I'm going to stop here for this video.